Welcome everyone to today's stream. I'm very delighted to have the seminar from Byrd, who's going to talk to us about a very interesting topic called relational programming and relational interpreters. So this is really a fascinating topic for me personally, and those people who are into kind of computer science or programming in general. I think they'll find this quite interesting. So with that, welcome, Will.
Thank you. I guess I should preface this by saying that what I'm going to show you is relational programming in the context of a language called mini-Canron. The with any term, it gets overloaded. So relational could mean different things to different people, like their relational databases, which of course are based on the notion of relations. So they are actually closely related. But the turns out there are lots of things people mean when they talk about relations or programming with relations. So especially in formal computer science and programming languages, that term is overridden. So I'm not claiming that to have a monopoly or the people I'm working with have a monopoly on the term relational programming. I'll show you a particular style of relational programming that I think is interesting. There are other forms of relational programming that I think are quite useful and becoming more widely adopted, like data log, which you can view as sort of an extension to the sorts of relational programming you have with SQL. That is definitely a relational programming paradigm or answer set programming, and those in between data log and answer set programming, I think you're seeing a fair amount of adoption now in including in industry. So that's a form of relational programming. Obviously, relational databases in the semantic web. There's a lot with Sparkle and RDF. That's a form of relational programming. But what I'm going to show you is Turing-complete relational programming based on constraint logic programming. And one way to look at this would be to say, if you're familiar with logic programming in languages like Prolog, Prolog's been around since the early 1970s. And there's this one great example of Prolog of where you can write append or concatenation of two lists, which in functional programming is kind of like a very simple hello world type program. You concatenate two lists together to get a third list. And so you have two input lists and an output list. Well, in relational programming, instead of having a function of two lists as input and a list as output, you blur this distinction between inputs and outputs, and you say we have a relation between three lists where if we have three arguments coming into this relation, the relation succeeds if the relationship between the three arguments is that the third argument is equal to the first two arguments concatenated together, and also they all have to be lists. So that's one way you can think about something like list concatenation as a relation. And the interesting thing is that as soon as you go from functions to relations, you are allowed to talk about unknown values, not just the output being unknown with respect to some given input, but you can talk about unknowns anywhere. And it becomes more like an algebra problem where you can say, well, what if I know what the output list looks like metaphorically, or the concatenated list? What if I know something about that, like the length of that list or the first three elements of that list? Then what can I say about the two lists that must have been concatenated together to yield that third list? So that's the great promise of Prolog, and Alan Kay has said that that's really the great idea of Prolog is that you can treat your programs as relations. There's been a lot of progress in functional programming for a long time, to the extent where I'd say functional programming has won in terms of ideas. No one designing programming languages now is unaware of functional programming and the idea of higher order functions and lambda, anonymous functions, immutability, those sorts of things, and lazy evaluation, like you see in languages like Haskell. So everyone's aware of that, even if not every programmer is using it. But lambdas now in Java, lambdas in C++, lambdas in Python. So functional programming ideas have won. Takes a long time to diffuse throughout industry, but the ideas are there. It's not going away. what happens after functional programming has won the war of ideas? Is it just more functional programming? Well, there's going to be more of that. It's like, okay, we'll throw more category theory at things and we'll have fancier type systems and dependent type systems and homotopy type theory. All those things are going to happen. They are happening. They'll continue to unfold. But at the same time, when you think of abstractions, when you think of properties you can get, invariants that you can talk about, in some sense, functional programming is still, not as abstract as what you get with something like SQL when you have tables where you can talk about unknowns in the table. So there is something very nice about being able to talk about tables of things and being able to ask questions and then fill in sort of the unknowns there. So that's the idea of relational programming is in some ways it's more abstract than functional programming. One of the nice properties you get with pure relational programming is that you can reorder your code arbitrarily and your program has the same semantics. This is not true in most programming disciplines. You can't just take your Haskell program and start just like reordering your code arbitrarily and have it mean the same thing. There is an order in which things happen, whereas in pure
Is that
constraint logic,
declarative versus imperative? Is it kind of like that? Not quite.
maybe. Well, I
Okay.
mean, sort of. I think the problem is all these terms mean different things to different people. Like, what is an effect? What's a side effect? What's an effect? It depends. It's sort of like what is referential transparency? Referential transparency with respect to what property do you care about? So I think these terms get thrown around. Uh, you could argue that relational programming in the form of pure constraint logic programming is more declarative than most functional programming. Now, there is a nice feature of programming in languages like Haskell is that you can do equational reasoning. This is partly because of laziness, and you can reason about sort of substitutions of variables, and that's very nice. And so I would call that a form of very declarative reasoning. And it turns out that Turing-complete constraint logic programming, relational programming does have some some real problems to the extent where some people say it's not really declarative. Okay, so and I will show you kind of the biggest problem that in my opinion, and I think in the opinion of most people who practice this sort of programming, there is a big issue, which is that conjunction or and is not commutative. It's commutative with like an asterisk, okay? So or is commutative, disjunction's commutative with a little asterisk, but conjunction or and is commutative with a big asterisk and has to do with termination versus finite failure. So we're in a
Interesting.
world where our programs can easily diverge because when we start filling in the values of variables. We're asking questions. It's like solving algebra problems, but we're usually asking questions over infinite domains. Okay, so depending on how we set up the problem, the algorithms, the things like that, and usually part of the algorithm is implicit, and it's a mixture of constraint solving and search. It may be that we end up doing a search over an infinite domain where we might not be able to prove that no answer exists.
Is that kind of like the whole team problem emerging
It
in this?
it's yeah, you can definitely see issues where the halting problem emerges. Even beyond that, though, there may be problems that are technically decidable, but where your encoding of the problem in a constraint logic programming setting doesn't take advantage of some cleverness that would make the problem decidable. So
Hmm.
it's the sort of thing where there's a very general mechanism that's used with this style of programming based usually on constraint solving like unification, maybe a different source of unification, which is based usually on syntactic equality of terms or extending that notion to maybe associativity, commutativity. idempotency, or not, alpha renaming of terms, lexical scope, things like nominal logic, nominal unification. They're different extensions of this notion of equality. And then maybe you also have constraints for disequality. Maybe you have constraints for arithmetic, like linear arithmetic constraints. You have some sort of set of constraints you're trying to solve. But the problem is if your domains are infinite and they're, usually infinitely many possible values you have to look at, as soon as you're in a situation where you have to look at infinitely many values and reject them all, then you're in trouble. Okay. So if there are infinitely many solutions, or if there's definitely one solution and you just want one solution and you have enough time and space, computing, if you have enough compute and you can wait long enough and you have enough memory, uh, then you can use a search algorithm that's complete, that's guaranteed in theory to find the answer. However, if no such answer exists, then either your program will run forever or until you run out of memory or whatever, or your program will finitely fail. This notion of finite failure, and so part of the trick of this style of programming is trying to write your programs where if there is no solution, your query will fail in a finite amount of time. But that's like an art. Okay, that is something that often requires real insight into the problem you're solving. And it may require doing things like coming up with or designing and implementing new types of constraints that are lazy. So the idea of the constraints are that instead of enumerating infinitely many possibilities that are ground, like if you could think of all the lambda calculus terms, lambda xx, lambda yy, and you could enumerate every single lambda calculus term, or you could enumerate every scheme program, or you could enumerate every C program, right, or every Java program. That's completely ground where you've picked variable names, concrete variable names, and things like that. But there are infinitely many such programs. What you want to do is be able to say, well, I can tell already that there's no completion of this partial program that has the property I want. So therefore, I can stop my search and reject
Yeah.
and say fail. Okay. So
Mm.
that's really the art of it. The art of it is when you're dealing with infinite domains, you're going to have to be clever in order to try to reject or fail finitely, um, and and not just enumerate. So there's this idea of generate and test, where you generate a possibility that's ground usually, and then you check to see if it has the property you want. It's like, I'm thinking of a lambda calculus term. Are you thinking of this term? No. Okay. Are you thinking of this term? And you just enumerate every lambda calculus term. Okay. Well, if there is no term that has that property, well, you could just keep enumerating terms forever. So that's the real problem, is generating tests where you have to enumerate infinitely many values and check them. Sometimes you can be more clever and you could prove, because you have some insight into the problem, that no such term can exist, and then you can just stop. Okay. And usually you need some insight into the problem domain, and sometimes you end up coming up with special constraints to help you fail finitely. You want to be as lazy as possible. You want to avoid, by laziness, I mean you want to avoid enumerating infinitely many elements in an infinite domain whenever possible.
Yeah. Mm.
Okay. So, and I'll show you all this stuff in a minute, but I just want to kind of set the stage for what we're talking about. So Prolog, came out in the early 70s, and it had this great idea of this writing your programs as relations. Unfortunately, from my standpoint, Prolog made a lot of design decisions. Actually, the very early version of Prolog was much more declarative. It was much more relational, but it ended up the implementation that ended up becoming popular was less declarative, less relational. These things happen. Okay, it happened
Was
also
was
with
that
Lisp.
a design choice to make it more usable, or like was it a constraint on just getting it out there? And practical or something like that?
Well, okay, so I don't know everything about the history of it. From what I've read, I don't want to throw anyone under the bus unfairly either.
Okay, okay.
My understanding is that this was like what we ended up with the first version of Prologue was basically a student project. A student implemented an idea, and the original idea had aspects that were more relational, but the implementation that the student didn't include all of that. I've seen this happen myself many times, so I'm not really surprised. But that seems like there's some historical things that happened. The other thing is, think of hardware in 1972, right? So there was obviously going to be compromises made. Like the search, instead of using a complete search, Prolog by default uses depth first search, which is very efficient in terms of space use, but is not complete. So if you're looking over infinite search spaces, it turns out you can go down like one part of an infinite search tree and never look at the rest of the tree. So maybe there exists an answer to your query, but you'll never find it. You'll go forever looking in part of the tree that doesn't have answers. Okay, so there are decisions like that that were made that were pragmatic decisions, but that compromise some of the logical purity or declarativeness. Another decision that was made was to not use the occurs check for unification. Um, to do first order unification over finite terms or tree terms, there has to be this one check to make sure one term doesn't include another, which means that it just keeps your terms finite. Otherwise, you end up with these what are called infinite rational terms, where a term sort of like includes itself. Um, you end up with these graphs that can point where nodes can point back to other parts of the graph and cycles. Okay, so
Hmm.
that's not supposed to be allowed in first order syntactic unification, which Prolog implements. But it turns out it's expensive to implement this check. So they're just like,
Hmm.
we don't do it.
Yeah.
Okay.
Yeah.
All right. So there are a lot of things like that. And a lot of times you can get away with it, but it does mean that the language, that plus 50 other decisions plus a standard library that was not designed to be relational means that in
Hmm.
practice it's quite difficult to do anything relational. There are people trying today to make Prolog more relational. Marcus Triska is doing interesting work. There's Scryer Prolog, and people are interested in the constraints now. Now there's more emphasis on constraint logic programming, and then there are also these sub-Turing-complete uh, relational languages like data log and answer set programming that have become popular. So, you're seeing a resurgence in interest, but my personal feeling is that Prolog, like standard Prolog, like ISO standard Prolog or whatever, that is just too hard to make declarative. The analogy I would make would be a programming language. It would be like trying to do purely functional programming in Python.
Hmm.
Okay. It's like, well, you can kind of do it, and Python has Lambda and stuff like that, but the Lambda's like, kind of has some issues. And more to the point, if you use standard libraries in Python
Hmm.
that aren't pure, that have
Hmm.
mutation all over the place, then it's like
You lose it.
you
Yeah.
might run into problems, right? Like if you're depending on sharing and immutability so that you can avoid race conditions and stuff like that, as soon as you start using other people's code that's not written in that style, you have to restrict yourself into how do you use the language. So that's the sort of issues you run into. So I think that Prologue, by the time you've turned Prologue into something relational, it's almost like you've turned Prologue into mini Canron. Mini Canron,
Hmm.
there's another way to look at it, is mini Canron sort of, okay, if you started with a language like Scheme and you want to do an embedding in it for a
Hmm.
pure constraint logic programming language, what would you end up with? And so that means we have to reject most of the features that you would have in a Prologue. Okay. And then the other thing I'll just say before we get into demos is that um, the probably partly because we're coming from programming language people, one of the things that we like implementing relationally are things like interpreters for Turing complete languages. So we can write a scheme interpreter as a pure relation in mini Canron. we can write a mini-Canron interpreter as a pure relation in mini-Canron. And what's interesting to me about that is that, scheme programs are not at all relational. So if you write append in scheme, that's just a function. It takes two lists and then returns a list. That's the concatenation of the two lists. However, if you if you write append in scheme and you call it inside of an interpreter for scheme written as a relation in mini-Canron, you can put logic variables from mini-Canron inside of the scheme code, and you can actually treat the append function as if it were a relation in Prolog or mini-Canron. It was like a really weird trick. And so you're like inheriting the relationality by writing an interpreter as a pure relation. And so you're taking a non-relational language scheme, and then you're able to treat it like a relation. And you're also able to do things like program synthesis, where you can put logic variables representing unknowns in the scheme code itself, defining append. You can put the logic variables anywhere you want, actually. And you can also do the same with mini-Canron code and mini-Canron, which is something we're playing around with more recently. So you can write, you can synthesize parts of mini-Canron programs that way. And this starts getting into things that are a little like inductive logic programming, but a totally different approach than inductive logic programming. So
Mm.
anyway, that's enough. I just wanted to give you a little background before I start showing things. And I just wanted to talk about some of the ideas. Okay. Any
Mm.
questions or thoughts before I dive into it?
What do you think about combination of functional and logic programming, like
Hmm.
curry?
Yeah, good question. I find that very interesting. The first thing I'll say is that mini-Canron is not a functional logic language. Okay, so it is purely a logic language, a constraint logic language. People tend to get confused by this because often mini-Canron is implemented in a functional language, scheme, racket, closure, whatever, Haskell. Um, but within the mini-Canron code, you're not allowed to use lambda. You're not allowed to unify lambdas. You're not allowed to, mix arbitrarily scheme code and mini-Canron code. That doesn't make sense. So it's almost like you have a monad. Basically, you do have a monad. We have this run interface. So we have scheme as the host language, and then inside the run, everything has to be mini-Canron. It is true that you can mix and match them a little bit, but you have to really be careful to preserve the types. And in practice, it's basically you're in the mini-Canron world or you're in the scheme world. Um, I'm very interested in things like curry. Now, there's also Mercury, and more recently, there's Verse, which Verse is also more like icon in some ways than like curry than it is like curry maybe. But I find those languages very interesting, and that's something I want to explore more. There's also inductive logic programming, which I find interesting. Um, so yeah, I would like to do something like curry and mini-Canron. Been playing around with some ideas recently. The most recent thing I've been playing around with, I'm calling Midori Canron. The Canron is Japanese for relation. Midori is green in Japanese. Anyway, it doesn't matter kind of where I got Midori from, but the idea there is by writing an interpreter as a relation that can handle both scheme and mini-Canron, because we can write a scheme interpreter as a relation, we can write a mini-Canron interpreter as a relation in mini-Canron. Well, what if we combine those? So what if we have something that's more like actual mini-Canron in scheme, where there's both lambda and there's also mini-Canron, and then you can kind of play games where you combine those in a kind of careful way. You still have to be careful with the types, but you are now allowed to play around with scheme and mini-Canron together. It's not something where you can do all the tricks in curry, but it allows you to kind of mix those paradigms a little bit. So that's something I've been playing around with recently. And one question is, okay, could we use that to implement curry? Now, this relational interpreter trick, while it's a very nice encoding of powerful ideas, also you pay a lot of cost for the interpretive overhead, and you have to re-implement unification and all these things. So there's another line of research to try to claw back some of the efficiency. Okay, and I also should be clear that I'm doing this work with many other people, and for the last 20 years I've been doing this work with other people, and originally started with Dan Friedman and then Oleg Kislyak, and then I came along, and I've been working with a bunch of people on Midori Canron and staged evaluation, especially Nada Ben, Michael Ballantyne, Jason Heeman, Rafi Sana. I'm going to forget a few people here, so I have to be careful. Greg Rosenblatt. So anyway, a bunch of people. Okay, this is not just me. There's a whole bunch of people who've been working for a long time on this. So I'm very interested in Curry. Very interested in functional logic programming, and I would like to have a functional logic, and I also like to have an inductive logic program, and also probabilistic logic programming. I actually think probabilistic logic programming is very important. So anyway, yeah.
I just forgot to ask you about probabilistic one too.
Yeah, so it's very interesting if you track the history of the AI lab at MIT. There was kind of the people who are very heavy on logic, like John McCarthy, but then there was like a very anti-logic reaction also. And I think to this day, there's a somewhat of an anti-logic reaction at MIT. And I think part of it is like, well, something like probabilities, probabilistic reasoning gets around a lot of the problems that you have with pure logic, because, with most logics, they're monotonic. And also, if you can ever prove false, everything's done. Or there's the old prologue joke, how many prologgers does it take to change a light bulb? The answer is no. Like, it just fails, and then you have no information, right? And so that there are all of these problems that people know about logic programming that probabilistic programming might help with. I've been working with Rob Zinkoff on and off for years, and we have a few versions of something called Prob Canron. Rob's got a new version based on particle filters that he works on periodically. But I think all of these things could be pushed much further. We only have a few people working on this. I will also say that there's a group that originally started at St. Petersburg State University in Russia, and JetBrains, and some of those researchers have spread out now to other countries, but they still have an active group. Dmitry Buchalov and his students and collaborators have been doing a lot of work in a typed version based on OCaml. So they have a language called OCanron, which is the typed version. Nada Min also did a version of minicanron. David Nolan did a version of minicanron and Clojure called core.logic, and then Nada Min did a version of nominal logic programming based on alpha canron called core.logic.nominal. So, people have explored this in different languages. And then Jason Heeman, who's another close collaborator, has did with Dan Friedman something called microcanron, which is like a core mini canron and 46 lines of scheme code that can easily be ported to any language that supports closures or objects. And now there have been thousands of implementations of microcanron in pretty much any language you can imagine. So you can do an implementation sort of in one sitting if you go through that paper. And so, so anyway, there are a lot of people who've been playing with this, but in another sense, in terms of people actually doing research today on probabilistic extensions, that number is like hovers between 2 and 0 depending on the year. Okay, so there are lots of opportunities here to jump in if you're interested. Okay, well, that's enough gabbing for now, probably. How about I show off some mini Kenron stuff, and then we can talk more as we do it. Okay.
Great.
All right. So let me just load. I'm in Chase Scheme right now. I'll load up mini Kenron. Okay. So Scheme, we're in Scheme right now. If you don't know Scheme, it's a Lisp. So we have things like self-evaluating literals, like 5. Hash-elf means false. Hash-t means true. Actually, anything in Scheme other than hash-elf is considered true. So we have self-evaluating literals like 5 and booleans. We also have, actually, we have symbols. So I can have quote cat, which is actually the same as QUOTE cat. Okay, so these are, symbols represent conceptual things, right? Okay, so so we have symbols and we have strings, which are not symbols. Those are different. So strings have parts, whereas symbols are atoms. They are sort of atomic entities. And then we have pairs and lists. So there's something called the empty list. So I can quote empty parens, that's the empty list. And also I can build up a list using something called cons, which is list constructor. So I can cons 3 on the cons 4 onto the empty list, and that gives me the list before. I have quote, so I can also quote the list. So quote of datum is datum. Quote of datum evaluates the datum. So you quote something, you just get it back. Now also I could call list if I wanted to. So there are different ways to create lists, but actually underneath the hood, these things are really pairs. Okay, so that's the same as 3.4 empty list. It's just they print out specially. So when you create cons, you actually get what's called a pair. You create a call cons. So we have a pair with 2 parts, and we can get the car, which is the first part. It's a historic name. And you think of it as first, and we can get the coder, which is the second part, which you can think of as sort of like the rest if it's a list. Okay, so we have lists. We can tell if a list is null. Okay, and we also have Lambda. We have the ability to, create anonymous procedures. Okay, so Lambda XX, that's the identity procedure. We can do things like add numbers. In Scheme, we have prefix notation. Okay, plus itself is just a variable. This is not special syntax like in Java. So plus is just a variable that's bound to a procedure that knows how to add numbers.
Question?
Sure.
Why did the empty list return null?
Oh, so like when I did so when I did null question mark of the empty list.
Mhm.
Yeah, okay. So in old versions of Scheme and in some versions of Lisp, there's a special symbol called nil. In R5 Scheme and beyond, there's just the empty list. So null just means is the list empty. So if I put something in the list, then it's not empty. It's not null. I don't know if that answers your question or not.
It's basically in this context asking if it's empty.
That's right. Is this an empty list? And you could also let's see. What happens if I put in 5? Okay, so 5 is not an empty list either. So it's like, is this thing a list that is empty? Okay. Now there's also a pair question mark. So there are various types of type predicates. So I can ask, is 5 a pair? No. Is cons of 5 a pair? Yes, it is. Okay. So they're pairs. There's also list question mark. So I can ask, is cons 5 a list? No, it is not, because a list has to. There's an inductive definition of a list. It basically has to end with the empty list. If you think in terms of cons pairs, it's like a list is either the empty list or it's a pair whose coder is a list, a proper list. Okay, so this is saying this is a proper list. Okay, so we have types and we have number. I'll just show you I'll show you the other ones that show up. So we can, is that a symbol? Yeah. Okay. Is it a number? No. We can give names to things a couple ways. We can define f to be lambda XX. Okay, so now f. So I've globally defined f to be a variable that refers to this procedure, which is the identity for procedure. I can apply f to plus 3, 4, and I get back 7. I can also just do anonymous procedures and apply them. So in Scheme, the parens always mean procedure application. So these outer set of parentheses mean you have a procedure application or application. There's an exception to that rule, which I'll show you in a second. But in this case, it means we have a procedure application. So And we don't have to give a name. We can have anonymous procedures. The exception to that rule is that if we have something called a special form, like let, I could say let x be plus 3, 4 in body, which is times xx. This outer set of parens does not represent an application or procedure application because the first symbol here, or first identifier, is what's called a keyword. Okay, and so you can see that Emacs is typesetting this in blue. So let, lambda, things like that. These are not procedures. These are not variable names bound to procedures. These are special syntax. And one of the nice things about Scheme is that you can extend the syntax using what are called hygienic macros. But that's basically, kind of the rules there. And I'll just show you there's one other special form called letrec, and let's just use it to define append. Okay, so I'm saying append is going to be a procedure. This will be a recursive procedure because Scheme supports recursion. And so we'll have L and S be our two lists, and then we will have an if expression. So we'll say if L is empty, return S. Otherwise, we will cons the first thing in L to the result of a recursive call, and on the rest of L to S. Okay. And then I will say, let's say within the scope of this append. So only within the body of this letrec will append be bound. Now, append, there's this append that's top level, it's already built in, but I'm defining my own append. I could call it my append if I wanted. So let's just say we've got ABC, list ABC and DE. We can append those together and we get ABCDE. Okay, so we're allowed with letrec to define a value, almost always a procedure, and that procedure is allowed to refer to the name append. And it's only bound, the append is only usable within the body of the letrec, basically. Okay, so that's the basics of Scheme. We can define recursive procedures. We have this if thing. One last thing I'll show you that I think is probably useful to know for context is there's something called con, which is McCarthy's conditional operator. And this is because it's so often that you have nested ifs that get really annoying. So instead we can add, tests. We can say, well, if L is null, then return, I don't know, return 3. I'm just making up dumb stuff. And if, L is a pair, then call F on the car of L. Else, return hash F. I don't know. You can make something up. But this is equivalent to having nested ifs. Okay, so this is the
Switch
test
statements,
part.
something like that.
If it's more
like-
general, you can have arbitrary predicates. And so you have a test position and you have return position. And actually, syntactically, it has more fanciness, is more extensions. But you could just think of it as sort of nested if. So you could compile this, or you could write a macro that literally turned this into nested if expressions, where you would have arbitrary tests. So here's an arbitrary test. So we could say, so that would be equal, or syntactically equal to if I said if, null L, then evaluate the 3. Otherwise, if pair question mark of L.
In
That-
Murzin, we usually call just which. It's called which statement.
A which statement. Okay.
So does it go through like does it find the first true one and evaluate that and return? Or does it kinda
Yes,
keep
that's
going and
the
return,
way
like,
to think
all
about
the
it.
things that are true get returned?
It's going to evaluate the tests in order of each clause. So these are con clauses. This is a clause. This is a con with 3 clauses. It can have, it has to have at least one, but it can have arbitrarily many beyond that. And so the test gets tried, evaluated. And if the test evaluates to a non-hashf value, because hashf is the only false notion in Scheme, then the sort of the consequent part is evaluated, and that value is the result of the cond expression itself. But it's just syntactic sugar in a way. Like you could literally just turn it into nested ifs, and it means the same thing. There are some extra syntactic extensions to cond, but that doesn't matter. So anyway, you will see that we have something in minikenrin called condi that syntactically resembles cond. It's sort of historical because we're very scheme centric when we were doing this original work. So I figured I'd show you that just so you're aware. And then the last two things I'll show you is we can have pattern matching. We have this match or p match or whatever. So we have some pattern matching. Actually, I wanted to show you that. That might come up at some point, but if so, I'll explain it. And then the last thing, which I don't know if I'll need to explain it or not, but I'll just go ahead and show you because if you ever want to read a paper on minikenrin, this is probably important to understand. There's something called quasi-quotation. Okay, so there's more than one type of quotation in scheme, and a type of quotation we use a lot is quasi-quotation. This example is due to Dan Friedman. So we might want to build up a list structure, which is something like, list of quote Mary, quote had, quote a, and then here's the adjective, lamb. Okay, so here I'm quoting Mary had a lamb, and then the ADJ is just a variable reference. So we let bound ADJ to be the symbol little. And then when we evaluate that list, we get Mary had a little lamb. That happens so often in scheme, and especially so in minikenrin, that there's a special shorthand for almost constant data where we have this back quote or quasi quote. Okay, that means everything within the quasi-quoted structure is quoted unless it has an unquote in front of it. Then it's treated as if it weren't quoted. So this has the same value. The reason this comes up so often is if you want to do metaprogramming in it's like scheme, let's say, what you'll often end up doing is you will often have something like a lambda term, which is quasi-quoted. You're representing, some syntax representing a lambda expression, and you might end up with something like that you want to evaluate. And then that means that this x can be, we could say let x be the symbol y if we want. Okay, and then we can take this entire term and evaluate it, and then you can see that filled in the concrete symbol y for the variable name. And this often comes up with pattern matching. So if we're doing pattern matching, we might very well have a pattern that looks like this. We're matching some unknown term with something like this. This is sort of the general form of a single argument lambda. Has some variable name x. We don't know what it is. We might have a guard saying it's got to be a symbol if we're representing identifiers as symbols, and then we have a body. Okay, so that's kind of everything you need to know, probably, and then some. Now you can read papers and all that. Okay, so let's just get into it. Oh yeah, by the way, how much time do we have left? Do we have 15 minutes or do we have more than that?
No, you can go for as long as it's still interesting.
Okay. All right. Okay, so let's let me teach you minikenrin. Okay, so I can teach you minikenrin less time than I taught you scheme. So basically I taught you scheme. Let me teach you minikenrin. So minikenrin is, first of all, we're embedded in scheme. So we still have procedure application being prefix. We have this operator called equal equal, which is like an equality value. Okay, so let me just show you one thing that's sort of equivalent in scheme. So scheme has this notion of a built-in procedure called equal question mark that takes two values and will tell you whether or not they're equal. So the empty list is equal to the empty list, and it's recursive, so we can say this sort of structure is equal to this sort of structure. That's fine. And if I change part of it, then I get back hash f instead of hash t. Okay, so that's a notion of equality, syntactic equality in this case. And so in minikenrin, we have something very similar except it's called equal equal, and this is a relation instead of a function. It either succeeds or fails. We don't get back hash C or hash F. It either succeeds or it fails. Now, if I try running this, I get back a procedure because mini-canron is an embedded DSL, usually. It's an embedded domain-specific language, is how it's usually implemented. You can write a compiler or standalone interpreter or whatever, but usually it's embedded in a host language. So we need some sort of interface operator. And the standard interface operator is called run. Okay? And you could think of this as sort of the monad that wraps, the mini-canron world and keeps it outside, or inside of the host world. Okay, so inside the run, this is mini-canron code. Outside the run is scheme code, if you want to think of it that way. And the syntax is saying, okay, we want one answer if it exists. We have this notion of what's called a query variable here. We can have as many query variables as we want. We have to have at least one. Here we're calling it Q, this by convention. And so basically we're saying for which values of Q, if any, is it true that these two lists are the same? They're syntactically equal. Now the answer would be, for which value of Q is this true?
None.
None? Okay. Oh, yeah, you're right. Okay, that's right. Okay. That's good point. You almost got me. All right. So we get back the empty list. I mean, it means there are no value, there are no assignments for Q. There are no substitutions that you can give to Q to make those two terms equal. Okay. Good one. Okay, how about that one? Would you believe that one?
Yeah. It's like
Okay.
any-
So what
but it's
for any?
infinite.
Yeah, for any value Q. And the way we
Yeah.
represent that is with this like kind of funny looking notation. Okay. Where we have an underscore, dot, and then some number. And that's because we can have multiple variables that come back. These are logic variables or unification variables. So Q is like a unification variable. We're saying for any value Q, I mean, Q never became instantiated as part of this computation. So you can think of that, well, for any Q, it's true that these two lists are the same. Okay. Now, I can put a Q inside of this computation. Inside of the query, it makes it more interesting. So now I'm saying for which value of Q is it true that Q is equal to that list? Well, for when Q happens to be this list. Okay. Now notice that we have parens wrapped around it because we get back a list of answers that metaphorically represents a multiset. Okay. So that's half of mini-canron. You've seen half of mini-canron. I'll show you one last thing here, which is if I wanted to unify Q with the list containing Q, that actually fails. We don't get back an assignment for Q because Q would have to be infinite. This is what's called the occurs check. So we maintain the occurs check, we enforce the occurs check. Like I said at the beginning, Prolog doesn't by default. Okay, so that's important to know. So now you know half of mini-canron already. We have run and equal. I'll show you the other half now. So we're going to have cond, which is syntactically like McCarthy's cond I showed you. And we're going to have two clauses, say, in this case. We can have one or more clauses. And we can say Q is cat, or Q is dog. Okay. This, in the cond world, with McCarthy's conditional, we would try the clauses in order. And there would also be a difference between the test and the value return. But here we're in a relational setting. Okay, we don't have inputs and outputs anymore. We just talk about things like the query variable, what's bound to the query variable. Also, there's no notion really of which clause should be tried first, or why would we only try one clause? We can try as many clauses as we want. So that's a big difference between this and an if or a cond and scheme. So when we try running this, we're asking for which value of Q, or give me one value of Q because it's run one, for which either, now it's an or, this is logically an or, either Q is a symbol cat or Q is a symbol dog. So, okay, here we go. We got back cat. If I want a second answer, I can change it to a run two. We tried both clauses. Both clauses contributed values through successful unifications with Q. Okay, no problem. I can have as many values as I want. If I want to ask for all the values, I can change the run two to a run star, or I could ask for run three. That's fine. I still only get two answers back. Okay. The something worth thinking about something worth being aware of is that the syntax of the kandi is really a disjunction or an or between the clauses of a conjunction. So here I can change this to X and Y. So I've changed my query variables. So I don't know, say mouse. So I can write queries like this and kandi clauses like this. So here we have two kandi clauses. In one clause, I better change this. How about that? In the first clause, I'm saying that I'm asserting that X is the symbol cat and Y is the symbol mouse. The second clause is totally independent of the first clause. Okay, so any association or unification or quality of Y with mouse, that has nothing to do with this clause. These are independent of each other. These are like many worlds interpretation of quantum mechanics, right? These are different worlds. Universe split off, okay? There's a world in which X is a cat and Y is mouse, and there's a world in which Y is a dog, and we don't know anything about X. Okay. So we have a conjunction within the clause and we have a disjunction between. And we're allowed to nest kandis. We're allowed, no problem. Okay, so we get back to answers. So X is cat, Y is mouse, or X would be anything, and Y is dog. All right. And then I will show you the last part of sort of the core mini-canron. We have a couple constraint extensions that turn out to be useful, but I'll do this. I'll show you just this last operator. So, if we wanted to, we could say, well, we only have one query variable, but maybe we want to introduce some local variables, some local query variables. This is pretty common, especially in when you're defining like recursive relations, that kind of thing, like helper functions, helper relations. So you can use fresh to introduce lexically scoped variables that are bound to these unification variables. Okay, so X, Y, and Z really are scheme variables, are lexically scoped, but they are associated with these logic or unification variables that we can call equal on. So I can do things like this. How about all right, so here's a good one. I'll make this a run star. Okay. Any idea when I can get back here?
Are gonna just be XY gonna be returned like literally? Right?
Okay, well,
Just
can you tell me exactly what would be returned? Like what
a
will I
list
say?
with a list with a single with one list is with a list of XY and another one is ZZ.
Okay,
Right.
now if I had done a kandi,
Yeah.
that might have been the case. However, what I should say is that there's an implicit fresh and an implicit conjunction within the run. Okay, so there's a conjunction here, and within the fresh there's a conjunction as well. So this is an and. So I'm saying it's the case, or I'm asserting that Q is the list XY, and also that Q is the list ZZ. Okay, now, so what can you tell me about the answer, given that this is an and of these equalities? These are equality constraints that I'm writing, okay?
It's just list of this any thing that is
Yes,
the same.
and they're the same. So notice the number is the same. Okay, 0, 0. Because if I were to remove the second unification, then X and Y could be different. But in the second unification here, I'm saying Q has to be ZZ. So that forces X and Y to be the same. Okay, so I can make it more concrete. I can say, here, I will then say that Z is 5. Okay, so now what we'll get back?
List of 5, 5.
Yeah, list of 5, 5. Okay,
Yeah.
all right. Now, remember how I told you I can reorder things? Watch this.
Yeah.
Okay, means the same thing. Same thing with the kandi. If I go back to the kandi example, right? if I can reorder the conjuncts and I can reorder the clauses, which are like the disjuncts, I still get the same set of answers, or multi-set of answers, really. Okay, they're produced in a different order, but if you think of these as a set, if the answers are finite, then it's just like they might be reordered. Okay, so it's like a permutation. So
Can
it
you
means the
just,
same thing. Sorry.
in the previous with the Z example, can you just in the query list of query add X and Y, those fresh variables? Can you query them?
You mean like put them up here?
Yeah.
Yeah. So let's say now. So if we're gonna do this, so what do you want to do down here? I guess. What
No,
do you?
just wanted the
Yeah.
same example to get more
Okay, but
explicit.
we need like a Q or something. I mean, here's what I could do. I could say list XY.
Well, we could have listed Q2, right? Q and XY, all three together.
Oh, you want Q, X, Y, all three of them up here? Okay, sure.
Yeah.
Okay, and so then you want this to be Q of ZZ?
Yeah, like it was before. So
Okay, so what do you think we'll get back?
I don't have XY anymore. You had
Okay,
another.
so I'm sorry, I think I'm getting confused. Okay, tell me how to change this or what you want.
Oh, just the complete previous example when we just
The
had five
complete
files
previous
around.
example. Okay.
Yeah,
So,
you just in your
right.
query variables just add XY.
All right. So let's is it this one you want or the one where we had a 5?
We do 5.
Oh,
Okay.
this one right here.
Yes.
Right. Okay.
Yeah.
So okay, that works. All right. So how do you want me to modify it? You want me to put XY up here?
Yeah, just to see them, right?
Okay. And nothing change nothing else. Is that the idea?
Yeah.
Okay. So what do you think will happen? That's a good example.
List X and Y too, which are also 5s. So there's gonna be more 5s.
More 5s. More 5s. Okay. I disagree. I disagree.
Okay.
Same number of 5s.
I see.
Okay, so now this is a great example, though. This is a great example. All right. So why? First of all, we get an answer. We get one answer back. Okay. So we get one answer back, and the answer has Q, X, and Y. The values associated with Q, X, and Y. Well, we understand why Q is 5, 5, right? Well, maybe not.
Yeah.
I don't know. But X remains fresh, and so is Y. They're not associated with this. Why is that? It's because we have shadowing. We have lexical scope. So this X is not the same as that X.
Yeah.
So inside here, Q is associated with this X and this Y, which are introduced here. Okay, so we could alpha rename. So we could rename. I could call this X1 and Y2 or Y1 or whatever. I could, or like if I were writing a compiler, I might do something like that. Okay, and it has the same answer. It's because we're allowed to have shadowing. And it's because in Scheme, you're allowed to do things like this. You can say let X be plus 3, 4, and then you can say let, X be 7, and then you can say, or actually, let me make it 9, and then you could say times XX. Okay, so it turns out that the innermost X, this X has nothing to do with that X.
Yeah.
In this
So
case,
fresh
right? So
is
this
just
X is bound to this X.
So you have fresh just for scoping the variable.
That's right. That's right. So Dan Friedman says that scope is everything. So mini-Canron is based very heavily on the idea that we want to preserve lexical scope. Now, Prolog does have lexical scope, but it tends to be more implicit. We've also been doing a lot of work on nominal logic programming for the last 15 years or so, and I'm working right now with Matt Leakin, who did his PhD on alpha ML, which is a constraint logic language for nominal logic programming. He did for his PhD under Andy Pitts at Cambridge. We've been playing around this last week on revisiting what it means to do alpha equivalence and capture avoiding substitution for lambda calculus and all that in a language like mini-Canron or alpha ML. Turns out that that's very subtle. Okay, this this sort of lexical scope at the logic programming level, if you want to encode it in a logic program or constraint logic program, is very, very subtle, and you might need special support, like a special type of unification, like nominal unification or higher order abstract syntax. You might need higher order unification or pattern matching. So there's like lambda prolog, there's alpha prolog. So people have created entire logic programming languages with different notions of unification to handle lexical scope. But here we just get this type of lexical scope just because we're embedded in scheme. And this fresh is going to turn into a let, really. Like if so here's one thing we can do. I told you that we have hygienic variables. So I can expand this code. Let's see what this expands to. Oh, whoa. Okay. So this is the actual code. That's what actually is turning into. Now we can say print. There are different ways we can do this. We can say print gensim -f, make it a little less difficult to read. But that's what it's really turning into. And yeah, so if I go back to the old version where it was X and Y, if I expand this, if I look for X, yeah, so here's a let with an X, and then here's another let with an X. And just through the scoping rules of scheme, the innermost X will shadow the outermost X because of the semantics of let. So those will be different variables.
So it's already, is this code already includes like the search, right? Or just
This code does include the search, this expanded code, although minicanron is a mixture, like the embedding and scheme is a mixture of hygienic macros and procedures. So the search is here. However, part of the search is going to be in the form of functions that are already defined. So you can't see the function definitions because in scheme those are opaque. But like you can see, this take, that means that we have streams. So we're implementing the search in the form of streams. We actually don't do any backtracking. So we have to pull from the stream. So you can see take here. You can see sort of the starting empty state. So there's a variable defined for the empty state. And you can see that we're playing different games of state. You can see a unification here. You can see that equal, we're passing in this state. So you can kind of see how we're threading things through and what the types actually are. So the type of a goal in minicanron is going to be a function that takes a state and returns a stream of states, potentially infinite stream of states. And we have an interleaving search that allows us to, a complete interleaving search that's biased towards earlier disjunctions, which is good in some ways and then, causes problems in other ways. Okay. So let me just show you a simple example. I'll show you the hello world, which is the append. So let's say, let me do the letrec version. Yeah. So let's say, no, I'll do the fine. Let me see. I'll do appendo. Yeah. Okay. Let me do the letrec version. So I'll say appendo. So that's our convention that relations should have an O. Kind of looks like a little question mark the way we typeset it in our book. And so our appendo relation is going to have 3 arguments instead of 2, like for append. And so now we have a condi. So these are all things you've seen. And so we'll say, now we don't have null anymore. That doesn't make sense, but we can unify L with the empty list. And that works even if L is a fresh variable. It'll just make L the empty list. And if L is ground, well, the unification will either succeed or fail. And if that's the case, then L plus S, which is the variable name I'm calling for the concatenated version, we'll just say that that's the same as L. Unify those. And then here I'm going to do a fresh, 80 res. And I'll say L In this case, if L is instead of the empty list, if it's a cons of A and D, which stands for car and cutter, in that case, L plus S is going to be another cons. That's going to be cons of A onto sort of the residual or the result. And how do I get that? I get the result by doing an appendo, a recursive call on D S res. Okay, so that's my definition of appendo. And within the scope of that LUTREC, I could also just use a define whatever I want. Doesn't matter. So I could say run star Q appendo ABC DE to Q, and then I get A, B, C, D, E. Okay. And then the fun game I can play is I say, well, I know that when I concatenate these lists, I get A, B, C, D, E. All right. And I can test to make sure that that is consistent. So I get _.0 for my query variable Q. That means that we succeeded without associating Q with anything. But then, of course, I can do things like put Q in an argument position. And it's like, oh, okay, well, Q must have been DE. And I can do things like say, well, how about we have X and Y? And so I could say, well, give me all the pairs X, Y, for which when I concatenate those lists, I get A, B, C, D, E, and it turns out there's 6 of them. Okay. Now, this program, which is basically the standard Prolog example, the sort of hello world of Prolog, this program already illustrates some nice things about relational programming and some problems and in terms of the declarativeness. So I can once again reorder some of the code. So I can reorder the order of those 2 unifications. I can reorder within a unification. I can reorder the Kandi clauses, and it still works the same. Okay, so that's great. Try that with your programming language of choice. Most won't work very well. However, if you're careful, or if you're paying attention, you'll notice I put the recursive call last within the fresh. So this is a conjunction. So what happens if I move up the recursive call earlier? Okay, so I'm going to change my run to a run 6 because I know there's 6 answers. I still get the same 6 answers back, maybe in a different order, but it's still the same. But what happens if I ask for 7 answers? Then come back. So what's happening is it's searching forever for a result that doesn't exist because it's going into the recursive call without knowing the structure of L plus S or L. It doesn't know that L plus S or L have to be pairs, or I shouldn't say knows, but the problem is the appendo has to succeed before we try these other goals. Okay, so this is the Achilles heel of Turing-complete Prolog style logic programming, is that conjunction is not commutative. There are different attempts you can make to try to get around this problem, and we've tried a bunch of attempts. Other researchers in the Prolog world have tried a bunch of attempts, but this is the problem that you run into. Now you can try to be lazy, you can try to add constraints, you could try reordering dynamically, you could try to statically figure out which order to use, you can try adding bounds to the size of terms, you could do a zillion things. But ultimately, at some point, you start running into problems. And also, because this is a Turing-complete language now that we have recursion, you can encode things like Hilbert's 10th problem, which are undecidable. You can like trivially do that sort of thing. So there's sometimes where you're just encoding undecidable problems. And then there are other times where, well, actually it's perfectly decidable, but the way the search works and the way the fact that conjunction is not commutative means that you're searching forever and you don't have finite failure. So sort of the simple rule is, well, put your recursions last in a conjunction. But the problem is if you have multiple recursions, which is often the case, there is no ordering that's optimal. So we've got a bunch of tricks we use, but no one, to my knowledge, has ever solved this really for constraint logic programming. So we've got hacks, but this is where insight into the problem and coming up with new constraints turns out to be important.
A couple questions just on that
Sure.
where you are now. So conjunction junction, what's that function? XOR?
Sorry, conjunction and disjunction. Sorry, what? Conjunction, junction. Okay, yeah, maybe I'm not being clear here. All right. So we have two Kandi clauses. Okay. So this is an or on the outside. So either clause can succeed independently. They're totally independent of each other. Within a clause, that's a conjunction. That's an and. Okay. So we're saying that these things are both true at the same time. These equality constraints both have to be true simultaneously. Okay. And then here within a fresh, that's also a conjunction. So we have some sort of implicit type things. It's partly just based on how scheme works. So cond is a disjunction on the outside, and within the cond clause, you have a conjunction. Lambda or begin or let have like a conjunction sort of in scheme. It's not exactly the same, but it's like a sequencing. So we're punning a little bit. We also can make everything explicit. So if you look at microcanron, everything's made explicit in terms of conjunction, disjunction. Okay.
I had a quick question about the recursive things. I mean, recursion tends to be like a major issue all over programming all the time.
Yep.
There was an interesting implementation of how to handle that in Bend, which was the high-level coding language for HVM2.
Yeah.
And what they did is they had like this unrolling of, and then the data structure itself had some kind of structure that every time there was a call in it, you had to what is it called? Nick, do you remember? It was something like you had to unfold, you bend them together, you bend them up, and then
Or they have those are just lazy nodes that they have to expand. I don't know what do you mean exactly.
But the point is, all the loops have to have that structure. That you cannot have a loop that just runs infinitely, I think, in the Bend implementation. Like there has to be you have to unfold the structure, the data structure.
There are, I'm not sure. I'd have to see this. I mean, there are lots of approaches where you want to bound the computation, so you unfold a loop or unroll the loop a certain number of times, and then you have like some sort of bound on it. And you say, okay, well, I'll have sort of bounded amount of computation, and I'll say, well, I'll unroll this recursion, this loop 4 times or something like that, right? And then you could do like an incrementally deepening depth first search or something like that. And it's like, I'll keep unrolling it one more step. And then maybe you just put a depth bound, and if you can't find the solution within a certain depth, you cut off the search. Okay, so there are all sorts of things like that. You can also try to statically prove properties. You can do things like look at whether or not the arguments are decreasing according to some measure monotonically. There's a whole bunch of things you can do to try to tame it. And certainly you can put restrictions onto the computations or to your relations to make sure that they're not going to diverge.
But you're just limiting yourself dramatically by doing something like that.
Yeah, it's like you could always do, add a type system that ensures that you can't diverge, like simply type lambda calculus is strongly normalizing. So you could do stuff like that. But if you want to remain general purpose, right? I mean, if you make everything general purpose and you're Turing-complete, well, then guess what? You've got the halting problem, right? So you're kind of, you could try to tame it. Like Olin Shivers says, always use the weakest language you can get away with. So if you were, trying to do something with a simple graph traversal, mini-canron is probably way too powerful. Like you'd probably want to use like a data log with bottom-up evaluation or something like that. Or if you were using mini-canron, you probably want to add tabling, as like sort of memoization for relations to make sure that you don't keep going around the same loop forever, those sorts of things. So, but in general, if you want to do arbitrary computation that could diverge, well, guess what? So there are lots of ways we can put bounds on things to guarantee termination. It's just like sort of like, well, if you're programming in Java, there's no guarantee your Java program terminates, right? So you can always work in a weaker language. Like, hey, guess what? Everything's a regular expression. Okay, well, fine.
My Java programs always terminate because at some point it'll crash.
Well, I mean, you could just like loop forever, right, and not increment anything. You won't, and not allocate memory, not bump up a pointer, and that should keep running, at least in
Is
most
it
languages.
this might be too theoretical and I might be distracting a bit, but is there something to say about like the fact that something is Turing complete kind of requires infinite recursion to exist for it to be Turing complete?
Yeah, I mean, there's something like that, right? So if you look in lambda calculus, the reason simply type lambda calculus is strongly normalizing is that you say that self-application isn't allowed. Okay, so it depends on your computational formalism.
Mm.
If you know, like for lambda calculus, the way you get recursion is through self-application. So you have things like if you look at the Y combinator or the Z combinator for the call by value version, you'll see that there's self-application, or the omega combinator. You know, the omega combinator is based on self-application. If you look at the Y combinator, you can kind of see the omega combinator like kind of peeking at you. But it's all based on self-application. So if you remove self-application, if you don't have an explicit fix or recursion operator, then everything's finite. Yeah, so
Or you
that
can
that's
have
one
primitive
intuition. Yeah, sorry, what's
Yeah.
it?
Or you can have primitive recursion, which is not Turing complete. Right?
Yeah, so you know there are all sorts of syntactic restrictions or other types of restrictions you can have, but yeah, if you want to be Turing complete, guess what? There are going to be programs you write. You can write. I mean, if you like a perfect example is we can express Hilbert's 10th problem, and Oleg Kislyak showed us that showed that there are different ways to express Hilbert's 10th problem
What
in
is
our
that
relation.
problem? Can you remind us what is this exactly?
Yeah, this is like the solution to Diophantine equations, right? So like this is connected to Fermat's last problem, last theorem, this sort of thing. So you have these Diophantine equations, and like Hilbert posed all these problems, right? The famous mathematical conference, and number 10 was coming up with, basically he didn't say these exact words, but he wanted to come up with an algorithm to solve arbitrary Diophantine equations. And then it turns out a Russian mathematician in the 70s proved that that was undecidable. There is no such algorithm. All right. So, but we can express that algorithm in mini-Canrid, because we have Turing-complete language, right? So that's like, well, you're expressing undecidable things. Guess what? So sometimes you can express things that are decidable. Sometimes you can be clever. Sometimes you can, do really, really smart things. But if you don't have any insight into your problem and you're just like writing stuff down, well, why would you think that you can terminate? Yeah. So, or you could write Collat's thing, conjecture. You can express that. Like, well, does that terminate? No one knows.
Mm.
Yeah. Okay, so this is basically what you've seen so far is like a core version of what you would have in something like Prolog. Okay, that's sort of, pure relational core. Now, the interesting thing to me is what if, unlike in Prolog, we take this idea of writing everything relationally seriously? Okay, so it's great that we can write append as a relation. Okay, that was done a long time ago in Prolog. But what if we want to write other programs that are more interesting, more sophisticated? And if you pick up a Prolog book, they'll show examples like this. And maybe for the first third of the book, hey, great, you can do all this relational stuff. And then the last 2/3 of the book will be, yeah, but you can't really do it. You can't do it for anything interesting. So let's show you all the dirty hacks. It's kind of like picking up a book supposedly on functional programming. We're like, look, you can be immutable and you can do higher order functions. And then they're like, yeah, but that doesn't really work. So here's like, here's just like mutate all the variables in global state. That's kind of how I feel about the Prolog stuff. Is like, yeah, they gave up on it. They didn't really believe in it. Whereas like the Haskellers came along, and they're like, no, we're going to commit. We don't know how to do I/O, but we'll commit to it, right? It's like, well, that's pretty bold. You don't know how to do I/O. That's kind of how I feel with mini-Canrid, right? It's like, okay, there are a whole bunch of things we don't know how to do. Oh, we also don't know how to do I/O, but like let's commit to it and see what happens. Because if nothing else, we'll probably come up with interesting problems to solve and innovations that way. So you commit hard to some approach, and you'll get stuck, and then you have to get unstuck. So that's what's going on here. So one of the games we played is writing interpreters for Turing-complete languages as relations, just like we wrote append. So I'll show you a simple interpreter here. So this is evalo. This is an environment passing interpreter for a subset of scheme. Okay, so if you're not familiar, I'm sure you all, know all about a val, and I'm sure Mathematica has a val, right? Mathematica probably has symbols and a val and all this stuff. It's like seems very lispy. So, in scheme, we can call a val, and we can give it a quoted, that is like, okay, so here's a simple example, like +3, 4. Okay, that evaluates to 7 in scheme. But if I put a quote in front of it, I just get back the list +3, 4, right? And then I can say, give me the first thing of that list, and I get back a plus, whatever. And then I can say, actually, what I want to do is I want to cons onto the coder. I say, here's the coder of the list, which is the rest of it, which is the list 3, 4. Actually, what I want to do is I want to replace that plus with the times. Okay, so I'm going to cons, the asterisk symbol onto what I get back. Okay, now I've got another list. It's still just a list, so I can get the car of it, and guess what? I just have the symbol. All right, it really is a symbol. I can ask symbol question mark. So I'm just doing symbol manipulation. There's nothing, symbols and lists, no big deal. But the cool thing is, because I have a val, I could say, well, take that list, and then let's just evaluate that list. Well, in this case, whoops, I needed the cons on. Yeah, it's just cons on, and there I get 12. Okay, so I can manipulate code. This is like a form of metaprogramming. Okay, Scheme supports many forms of metaprogramming. This is one of them. I can just shift symbols around and then evaluate the result. Well, if you look at eval, it's just a function. It's a function that takes one argument, or it's a procedure. I should say. It's not a pure function. It's not, and it's not a total function, certainly, because it can diverge. So it's a procedure. It takes one argument, and then if it doesn't diverge or give an error, you get back the result of the evaluating the expression. Well, what's the mini-Kenron equivalent? Well, we want a relation. Instead of eval, it's evalo. Instead of taking one argument, it takes two arguments. Great. So we can do our run example again. So I can say, I am going to evalo a quoted expression. And so how about, I will do like list of quote cat and quote dog. Okay. And I'll say that that list expression should evaluate to something. Oh, did I load? Hold on a second. I load my interpreter. Okay. All right. So just reformat that, make it a little easier to read. So we have some expression. Notice I put a quote in front of it. And I evaluate that expression in our relational scheme interpreter, and then I get back the list containing the list cat dog. Okay. In this case, there's only one value. That's no problem. Now, what are we going to do? We're going to play our standard game. So I'll say, hey, I have an expression exper. I'll just make it clear through the naming of the logic variable. And I want it to return a list, which is I love scheme. Okay. So let us generate an expression in our subset of scheme, which has lists and quote and lambda and application variable reference that evaluates the list I love scheme. Okay, well, here's one, just quote I love scheme. Well, that's true, and I can take that expression and just run it in Shea scheme, and sure enough, that evaluates I love scheme. But let's try something a little more interesting. How about let's get 99 of those? Okay, so here we have more sophisticated programs. So let me just grab this one. Now it's got some side conditions because these are very abstract answers. So I don't have concrete names for my variable names. So we have some side conditions. And also for the concrete values, like the quoted symbols, that's very abstract as well. So we've tried to abstract away as much detail as possible. But if I run this, sure enough, I get back I love scheme. Okay. Now, so that's like an emergent behavior. We didn't write a program synthesis tool. We just wrote the standard operational semantic style big step evaluator that you would write, in Scheme. Like if you're teaching programming languages to Scheme, you write a metacircular interpreter in Scheme. Well, we just wrote that, transformed it into Scheme. So Mini Cameron. Okay. There was nothing about it that was designed for synthesis, but you get synthesis as sort of emergent property. Now, there's a fun little example here. John McCarthy had this micro manual for Lisp that he wrote in, I think, the 70s or maybe early 80s. And it's like this 2-page description of Lisp. And then he has this, showing you about quotes and lists and that kind of thing. He has this little difficult mathematical type exercise. Find a list E such that value E equals E. So value is his eval function, okay? So he's basically saying we want to find an expression, E, such that if you eval E, you get E. And it's like a fixed point, okay? So this is Quine, as Doug Hofstadter calls it. So let's try doing that. So how would we write or how would we modify our expression here or call to evaluate to get back this program that evaluates to itself? What do we change here?
Well, we need equals, right? So
well, we can use an equal if you want, sure. So what? Okay, I'm just changing it to E to be like John McCarthy. Okay, so what tell me what else I change and yeah.
well, equals eval E and E, right?
Oh, you want to put an equal out here?
Yeah, in the beginning.
Okay. You have the right idea, but remember that evaluate is a relation. It doesn't take one argument anymore. It's a 2-place relation. So we don't need the equal. In fact, we don't put an equal like that. We just say, actually, it's that. It's just that.
Yeah.
Okay. Because the output is, or the value already is being unified with things. Okay.
Right. Yep.
And there we go. So this is the canonical Lisp. Well, it's almost. Let me rewrite the abstract variable name, the X, to make it easier. So this is the canonical Lisp and Scheme Quine. This works in Common Lisp also. Okay. So once again, this is just saying emergent. We didn't intend this. In fact, Stu Holloway pointed out, hey, you should be able to generate quines with the interpreter. Well, okay. So we wrote the interpreter, and then years later, someone pointed out that we can do this. So that's why I'm claiming that this is like an emergent type behavior. Now, I'll just show you one more since that's kind of fun. So you can also have twines, which are twin quines, P and Q, such that P evaluates to Q and Q evaluates to P. Now, every quine is trivially a twine. So we also want to make sure that P and Q are different. They're distinct. So we can add a disequality constraint saying that they are different. Okay, that's another constraint which I hadn't shown you before. And here we get back disequal things. Now, these actually aren't that interesting, so I'll show you one more constraint called an absento constraint, saying that one term does not appear within the other term. This is sort of like a variant of the occurs check. This turns out to be helpful for other types of things. And now you can see that, here we have a twine with a called list, and then you evaluate that and you get a direct application of a lambda, and you evaluate that and then you get your list again. So they go back and forth. And so you can generate, thrines as well or whatever. Okay, so that's the sort of thing that you can get. Now we can go beyond this. So let me load another interpreter. I will indulge you and I'll show you one last thing and then we can take a break. And then if you want to talk more, we can. If not, we call it a day. So I will load full interpret. This is an interpreter for a bigger subset of Scheme. And let us do the following. So we are going to once again call evaluate, but this is a more fully fledged evaluate. This is why I wanted to show you about quasi-quote, by the way. Okay, so we're going to evaluate some program. In the program we evaluate, remember when we wrote append as a letrec? And grab that. And I'm going to place it here. So this is important to keep track of, okay, because now we're kind of at different levels. Okay, we have a Scheme compiler, Shea Scheme, inside of SHA-Scheme, we have extended SHA-Scheme with hygienic macros and procedure definitions to create miniKenrin. In miniKenrin, we have written a program as a relation that is a scheme evaluator for a subset of scheme. Okay, so we have scheme in miniKenrin and scheme, and you kind of have to start telling them apart a little bit. Okay, so this is a scheme function that we are defining inside of the scheme interpreter written as a relation in miniKenrin running in SHA-Scheme. Okay,
Sounds like a scam.
yeah, that's right. Okay, so but the point is, this is not appendo. Okay, this is not the Prolog equivalent of the Prolog program. This is just regular scheme append, which I ran in scheme before, if you remember, right? And it's not a relation, and it only takes 2 arguments. It doesn't take 3 arguments. Okay, so I'm just going to run it, and sure enough, it runs because it's just a scheme program. Okay, nothing special, but we can do our favorite trick where we say, oh, well, the output has to be A, B, C, D, E. And sure enough, that's consistent. So now what can we do? Because this is a quasi-quoted expression, it's a quasi-quoted scheme program, I can go inside of the append call and I can put my query variable right there.
Hmm.
And I could have 2
Pretty
query
cool.
variables. I could have X and Y. I could say X and Y. And I could say, here's an X. And here's a Y. And I can say, give me 6 of them. So I have recapitulated the behavior of the relational appendo through writing an interpreter for a non-relational language. And now I can treat the functions or procedures in that non-relational language as if they were relations. I can do program synthesis to give them extra behavior that they didn't have before in just the original semantics, because I'm doing this synthesis trick with the relational interpreter. I can also go back to the first one, and it's like, well, if I ask for run 2, well, there's only one answer because it's list ABC. Like Q would have to be list ABC, but I can remove this quote here. And now when I run it, I see that I get a new answer, a second answer, which is a direct application of a variadic lambda. So what's going on here is that unlike with appendo, which could only take lists or logic variables representing lists, here I am inside of a valo, so I'm inside of a scheme interpreter. So what I'm doing is I'm synthesizing arbitrary scheme expressions that evaluate to the list ABC. And there are infinitely many such expressions.
Hmm.
But if I put a quote there, I recapitulate the appendo behavior because now it's just a quoted datum. So I just get the concrete list. I mean, it doesn't have to be concrete. You know, I can do this in such a way, like I could actually call list. Okay. I can make a call list, and then I can, or cons or whatever, I could call it cons, and I could say cons quote A to, you know, things like that. So I can play around with, you know, these different programs, and I can put logic variables anywhere I want. I can put logic variables in the code, in the definition of append, or whatever. Yeah, so that's another thing. Let me just show you that one too. So I can say ABC. Okay, no problem. And now what I could say, well, let's put the Q, I don't know, here. So here we're returning S. Well, I could put Q there instead. Okay, so now I'll synthesize part of the definition of append from examples. And if you do a bunch of optimizations to this, like Greg Rosenblatt did for Bartleman's system, you can actually synthesize the entire recursive definition of append from some examples. You have to speed it up, you know, by a factor of like 100 million to a billion, but you can, and then, you know, there's a bunch of tricks. Okay. I shouldn't even call them optimizations because sometimes they can make things run slower. So we have like this little tool, Bartleman. Let's see if I can get this running. See if you can see it. All right. I'm going to have to, I apologize for turning off my dark mode real quick. Let's see, appearance.
Thank you for warning us before you did it.
Yeah. Okay. So I don't know if you can read this as this is big enough. I don't know if I can zoom in with the screen sharing or if that causes a problem. Does that zoom in for you or not?
Yeah, that's good. Dugan can zoom in if necessary as well.
Okay. So anyway, this Barliman tool, yeah, let's see if we can get it without moving around. This Barliman tool allows us to have a partially defined scheme function. And then these uppercase variables with commas, those are like logic variables representing unknowns. So I can say, I want to append empty list to empty list, and that should give me back the empty list. Okay, so this is like test-driven development. Okay, so here it's like trying to fill in, saying A has to be append, B, it's guessing that this is a variadic, multi-argument, potentially multi-argument, or any number of argument lambda, and then it always returns the empty list. But we don't want that. We want, I can give it, like I can give it a concrete one that's ground if I want. Okay, and then it will have to, say, okay, well, I think it probably takes two arguments, and now we have a conditional, but it's still, a special casing. And so there are various ways we can try to get around the special casing. One way is to do just another example that's different. Another way is to say that we want the A and B to not appear in the answer. So, whoops. This is part of the thing, right? If your examples aren't right, maybe this is why probabilistic stuff is interesting. So now, it doesn't have the recursion yet, but it's not specializing. So another thing we could do, like I was saying before, is, let's see if I remember how to do this. And I think it's like, yep. And then, so these are a kind of like lexically scoped gensims or Skolem variables, if you want to think of them that way. So in this case, I'm making sure that these names that I'm choosing don't appear in the output. This only works, by the way, with certain classes of programs that don't inspect the results. So this isn't going to work in general for most functions. You have to use other types of tricks. 3, 4. Okay, and here you can see it came up with the recursive definition. It's a little hard to read, so let me give it some variable names so you can see the code a little more easily. Yeah, and so that's the correct recursive definition of append. Yeah. So anyway, there are all sorts of other things I could show you, but I think that was kind of like maybe a good intro to prime your brains about it. There's some challenges to make it fast. Yeah.
A lot of machine learning is sort of getting this function fit to the input and output, and this is getting a logical function.
That's right. So that's one of the questions: is how could you combine this sort of approach with machine learning, deep learning, LLM, things like that. And
There's
also,
actually a question. Yeah. There's a question there that's related. So I'll just ask it here for Richard, who couldn't make it. And the question was, why is program synthesis mostly academic and has not seen wide adoption in the commercial software development process? And then he said maybe something about super optimization and deep learning methods used to prune search spaces, etc.
Yeah. Well, I guess it depends what you mean by program synthesis, because now you have Copilot and things like that, which are maybe guessing. I don't know if they're complete synthesis, but they're more like smart completion, somewhat smart completion. Maybe not sound, but maybe a good guess. So yeah, I mean, that seems to have gotten some traction. I think formally verified or formally correct synthesis has a couple issues. One is, well, you're dealing with this exponential search space, and you better deal with that efficiently somehow, or you better restrict your problem really significantly. Another issue is the specification is tricky. So if you do input output examples, that's, people call it programming by example. Sometimes you do program traces, you do programming by demonstration, there are all these types of things, but they all ultimately come down to trying to make it easy for a programmer to specify the partial behavior. But these are partial behaviors, partial specifications, right? If you want to formally, fully specify the behavior of a function, usually the specification is longer or more complicated to write than the actual function itself, right? So there's been
SP
work
versus
with
NP, right?
yeah, it's just like there's been work on using fancy dependent type systems and refinement types to do program synthesis. For example, and it works. It does work in a real sense, and when your program synthesized is correct by construction. However, if you look, is like way harder to write the specification and to write the type than it is to write the program. Right. So that's part of the issue. Now, if it's something you really care about correctness, maybe it's worthwhile. But like how would you specify the correctness of Minecraft using fancy dependent types? I don't even know what that would mean. Or like Jerry Sussman gives the example, how would you specify that your chess engine plays chess well formally? I don't know what that means. So that's part of the problem. And then the other problem is still, how do you do efficient search? So I think there are interesting advances recently with like reinforcement learning, Monte Carlo tree search. I'm working with NodeMN and collaborators on this VerMCTS, which is verified Monte Carlo tree search, synthesizing things like Daphne programs based on Monte Carlo search informed by an LLM. There's been some interesting work that was shown this January at CPP, Certified Programs and Proofs, co-located with Popple in London, where one of the keynotes was on applying machine learning techniques to automated theorem proving, showing that at least in one case, with a average branching factor of 10, they were able to find a proof at depth 300. So arguing that 10 to the 300th power search space, they were able to find solutions. Whether or not those techniques will be applicable to program synthesis, I don't know. But that's one area that I'm very interested in is, the reinforcement learning seems to be helpful. Certainly if you look at how humans actually write programs, we can teach an undergraduate how to write append. We don't have to have them do a search where they do look at 10 to the 300th programs and generating tests, right? So there is lots of structure, and of course, you can do things like bias the search based on all the code on GitHub, which works pretty well if you're doing something simple in Python, maybe. How well this generalizes, I think, is still yet to be seen, and how to combine things in a way that works well. We've done some work with like n-gram based things. Did this with Michael Ballantyne, Rob Zinkoff, and Kanaya Shushima, where we were, taking corpuses of scheme code and just like doing basic counting. Okay, if you're inside of a let, what percentage of the time do you have a lambda here? What percentage of the time do you have a variable reference? Stuff like that. Using that to bias the search, that actually worked pretty well, and it was super simple. So there are techniques like that that I think are pretty lightweight that can be used to help a lot. I guess part of it is academics care about writing papers. As part of seriously, I think that's a very, very big problem. I guess the real question is, well, why didn't DeepMind solve this problem? I mean, they've made some attempts. So why aren't you seeing the big labs doing this for real? Microsoft Research has done some. The biggest commercial success has been flash fill. Microsoft Research added to Excel, You could do some synthesis of simple Excel formulas, but I haven't seen anything interesting yet. Yeah, I think it's coming. I think it's possible. I just don't think that the labs
Yeah.
like either believe it enough or put in significant resources. So.
It sounds like kind of how machine learning needed the compute to make it realistic. It's almost like if we need the optimization, we need the compute to be so optimized to be able to run search so fast that you could this becomes viable maybe. So if there was some new paradigm in,
Yeah, maybe, but I don't think it's just about the hardware. Like if you look at SAT and SMT solvers, yeah, they benefit from the hardware advances, obviously, but the much bigger advances from the algorithmic,
yeah, that's what I meant.
tricks that
Like,
people have used. Yeah.
yeah, that's what I meant. Like the foundations of how the things are computed. I mean, we had Victor Taylor on here talking about interaction combinators, and that's like a very interesting line of research because there seem to be some dramatic speed ups in running certain things because you have this like optimal evaluation and that kind of stuff. So perhaps searching for programs or program synthesis under those models makes, if you can bring it down by a certain order of magnitude, then it becomes easy for people to do it and then it will become more viable.
I'm optimistic. I think it's doable. And I think it's when we figure it out, we'll be like, duh, why why didn't we do that? Why didn't we get that working before earlier? I just don't think there are many people working on it outside of academic labs where literally people care about getting publications.
Yeah, and that's the trade-off because if you're in a startup or you have some commercial pressures, it's how much time do you spend researching versus just like
That's right.
writing the code to get the stuff out there. It's a dramatic trade-off.
That's right. But I think we're at the point now where I already expected to see significant breakthroughs. By now I'm surprised that it's been so slow, but I don't think it'll continue being so slow. If nothing else, if the LLMs keep getting better, you could use the LLMs to try to guide your search, and then use logic-based techniques or probabilistic logic. So that's what we're trying to do with like the Vera MCTS is using the LLM to try to guide some, combine that with like a Monte Carlo tree search. Like someone will figure out the combination, or the LLMs will keep getting better, or we can do. I mean, a lot of it's just lack of compute. So I working with Lisa Zhang and Greg Rosenblatt and Matt Might and other and people at University of Toronto, and the problem was they couldn't get GPU time, right? Because academic labs, like it's just hard to get compute. Like you're not at Google. We don't have like TPU clusters laying around. So that was it. Like we gave up on the project because we couldn't get GPU time.
Wow.
So that's the difference.
One more question here from Richard was he wanted to know about inductive logic programming and the work of Stephen Muggleton.
Yeah, that's interesting. And there's been a lot of interesting work recently with like Andrew Cropper, for example. Yeah, I'd like to know more about it as well. I think it's very interesting. So I've heard it described as machine learning people stumbled across logic programming. I don't think that's a fair way to say it. I don't think that's historical either, but it is kind of one way to think about it. I think what's interesting there is you have a background theory, you have positive examples and negative examples. So it's like not enough just to say whatever program you synthesize has to pass these tests. It also better not have this behavior. Okay. And then you have a background theory, which can be things like, here are some definitions that is possible to use. And then you synthesize, usually like a logic program, usually like a Prolog program. So that's what you're doing. You're synthesizing a Prolog program that covers all of the positive examples and doesn't cover any of the negative examples, and can make use of background theory predicates. And then the hot thing is predicate invention, where basically it's like synthesizing lemmas or helpers also that could be useful. So synthesizing a program, but then synthesizing all the helpers, one or more helpers that might make it easier, may make the program you're synthesizing smaller. So they've made a lot of progress with that. So yeah, I think that's really interesting. I think part of it is there's an answer set programming, data log, inductive logic programming, probabilistic logic programming, like the mini Canron stuff, the Prolog stuff. The communities, like, there's not a lot of overlap.
Mm.
Not a lot of overlap, and everyone kind of speaks different vocabularies. And I can tell you that the most brutal reviews I've ever had were from Prolog experts. And they usually the review usually is everyone knows that this is trivial, and also everyone knows it's impossible in the same review. And I understand their point of view. They'll say, well, yeah, we know we can do it, but it's like too expensive. That's kind of what they mean, I think. I mean, they'll say, well, you can never do it. You'll never be able to synthesize recursive programs, or you'll never be able to do this, or you'll never be able to do that. And then, of course, we figure out how to do it. So that's good. It's like a motivating thing, but that's like very typical. Is that we've actually had a lot more interest from the functional programming community than from logic programming community, and I think it's partly because my pet theory, is that the logic programming community was ruined by Prolog. The Prolog succeeded to such a great extent that it just like captured the community almost entirely. And so everything has to be in Prolog syntax, and then everything has to be horn clauses, and everything has to, like be some variant of ISO Prolog or whatever. If you look at almost all the papers, almost all the syntax for everything has to look like a Prolog program. And it's like, well, what if every functional program had to look like Lisp 1.5? You're allowed to make variants of Lisp 1.5. You're never going to have Haskell. You're never going to have like Idris. It's just like, and so that's I think where the community gets stuck. And so people say, well, I can do what you're doing in Prolog. It's like, okay, well, fine, go ahead. And by the time they've done it, they've like had to change everything built in Prolog and override it to make it more like mini Canron. It's like, well, yeah, you could do it, but the point is, like all of the defaults are hurting you. You have to change all the default behavior. So anyway, I think that's a problem. Fortunately, functional programming didn't have that problem. We ended up with a bunch of languages. I hope Haskell doesn't become too dominant. ML became kind of dominant for a while in academia. I don't think Haskell is going to be too dominant, probably, but that's my concern, is that functional programming will end up like logic programming, where everything has to be a variant of language X, and then we'll get stuck in the same way. I don't think that'll happen, but it could. But languages like Verse, I mean, they look quite different than Haskell. Curry looks quite different from Haskell, so I think it's okay. But I think the Prolog community really got stymied. I mean, they don't think that, though. They think it's all perfect. Everything's Prolog, everything's Prolog syntax, it's all horn clauses, it's all perfect. It's like, no, you're stuck. You've been stuck for 50 years. That's my perspective. I mean, they've done amazing things, right? It's not like they haven't done anything. It's given them superpowers, but they're still, in some ways, I think, stuck in a certain way of thinking. And if you do anything that's too different from that, they just sort of out of hand reject it.
I have a question. It's like you showed a bunch of scheme, and I know in scheme world there's like very famous Gerald Sussman work, like structured interpretation.
Yeah,
right.
Abelson and Sussman.
Yeah, and also functional differential geometry, which has like this nice definition, physical definition. So it's basically using scheme to define like equations, Hamiltonians, Lagrangian. And I wonder whether you can use functional logical programming in order to do some of the physics similar to this.
Okay, that's a good question. So part of the idea that functional differential geometry, and also they have another book on classical mechanics. And by the way, there's a new book sort of in that series, if you want to think of it that way, called SDF, Software Design for Flexibility, How to Not Program Yourself into a Corner, which is also an interesting book. But part of Jerry's point is that if you are learning general relativity and you're trying to learn, I mean, that's right. I got this gravitation book here, and you open it up. It's like, oh yeah, here's all the different notations all the authors use, right? So that's like kind of welcome to general relativity. But one of the things Jerry points out is that if you are a bright student who's curious and inquisitive, and you're learning calculus, you're like, what is this dx thing? Right? Like, what does that mean? Like, and like, am I allowed to divide this thing? Then what does this symbol mean? Right? It's like because there's all this lexical scoping, and there are all these rules that are only implicit in the notation that ended up being dominant. And mathematicians and logicians love taking shortcuts, and they love not writing things down explicitly. But when you're trying to learn the subject and you're trying to learn the notation and it's all implicit, you're really in trouble. And even people who don't want to be implicit, they can be tripped up. Like it took logicians a very long time to figure out the rules for capture avoiding substitution correctly for lambda calculus, that type of thing. It's very, very easy to get that wrong. It's quite subtle. In fact, that's why nominal logic programming exists. Is that it is so subtle that there's 20 years of research on trying to. In fact, I would argue that a fair amount of modern programming language research is on trying to deal with scope and binding. So there's locally nameless, De Bruyne. You can use straight combinator notation. You can use nominal logic. You can use higher order abstract syntax. People have figured out all these different ways to try to represent scope and binding in variables. And so part of the idea of the classical mechanics book and also the functional differential geometry is to try to tame the notation and to make all that stuff explicit so that you can talk about scope and binding. I haven't thought about either doing the classical mechanics or the differential geometry in mini-Canron, but now that you say that, that sounds really interesting. Okay, all right.
I would love to see some examples. Yeah.
Yeah, so would I. And yeah, I think recently we've made some progress on areas that might work. Now, one way we could potentially do it could be slow, is literally we could implement all of the scheme used in those books in a relational interpreter in mini-Canron and then put in logic variables where we wanted to do synthesis. That would be a way to do it. Another way would be to just extend mini-Canron with extra constraints if we need them, and just implement the language of the book as relations. It'd be interesting to try both ways, and then if you do this embedding where you write the relational interpreter for the language of those books, then you'd have to do like staged evaluation, super compilation, or whatever, collapsing towers of interpreters to try to get back your interpretive overhead. But that's also a very interesting research problem that we're looking at. Good question.
Yeah, very cool. Yeah, just by way of how we came across your work was we were looking at ways to handle the combinatorial explosion that happens with hypergraph rewriting when we're trying to visualize it in real time. And that's where Richard Assar was looking at mini-Canron to see if there was some kind of way that you could use it. Yeah. So
maybe. I think it depends on, okay, let me put it this way. We certainly know a bunch of tricks and techniques now for making certain things efficient or much more efficient than they would be. A lot of them are kind of special purpose. Obviously, if we had a bunch of awesome general purpose tricks that no one else knew, we would be, using them, and we'd be, telling everyone about them. We do have a number of techniques that we know of, and the literature is full of a lot of these things that might be interesting. One other branch that's very interesting is this whole reversible computing area. There's been a lot of work on reversible computing, and that is tied to some extent. Then speaking of like effects, losing information is an effect. So that becomes very important in quantum computing, for example. You can't just like clone information or erase information. But even in the classical world, classical reversible computing where you don't lose information is very interesting. And, so there's like all that work by Edward Fredkin and, Toffoli and all that. That's very interesting. And so turns out there's an interesting group of people who are interested in reversible computing and super compilation. And so maybe there's some weird things there, because when we're writing these programs so that we can write everything as relations, is there some way we can kind of mix the reversible computing as well? Would that somehow give us more leverage? I don't know. And then there's a whole bunch of things that we haven't yet had the time and effort to and engineering to try out yet. So I've got, I don't know, probably a few hundred experiments and implementation things to do. So I don't know. Maybe we know something that would be useful for what you're trying to do. I have to know more about your problem, but yeah, be happy to talk about it. And also you all are interested in hypergraphs, right?
Mm.
Yeah, and so I was talking to Greg Rosenblatt, and he said, well, hypergraphs are relations. So there's like a relational view of all this. So yeah, maybe. I mean, there's a whole bunch of. I guess does everything have to be Turing-complete? Could you use like a data log or an answer set programming approach? How about egraphs and equality saturation? Have you looked at that?
Yeah, that was one of the approaches, egraphs.
Yeah.
Yeah, there's some interesting work there, memoization, different things like that. I mean, at the foundational level, if physics can be represented in hypergraph rewriting, then it would have to be Turing-complete. Otherwise, we would not be in a Turing-complete universe.
Well, maybe we are in a
know?
Turing. Who said we are in a Turing? I mean, we've never built a Turing machine, right? Like all of our memories are finite. So maybe I mean I thought like the whole digital physics idea was that within any bounded volume there was only a finite amount of information that could be stored. So I don't know. I mean I'm not saying I'm convinced that's true. I just I don't know. It's an interesting thing, but hypergraph rewriting in general is interesting. Is there like Knuth-Bendix completion for hypergraph rewriting? Well, I don't know.
Maybe Carlos can comment a little bit as well.
What's that?
No, Carlos is our resident mathematician, so he does a lot of high arity science and looking at hypergraphs explicitly.
Yeah.
It depends on the
on stuff to do here. Yeah.
Is there Knuth-Bendix? What is the Knuth-Bendix? Completion?
It strongly depends on what hypergraph rules you define, basically. So it becomes a much more subtle question in general. And also, if hypergraphs are simply sets of subsets, that is one realm, but we're considering hypergraphs as being kind of generalizations of kind of combinatorial species networks. So it strongly depends on those things. I mean, all the research has been done on sort of formal rewriting theory, hypergraph rewriting theory, has led to similar results of you really need to specify what class of hypergraphs you're working with, and then you can start to claim some specific things. And the general flavor, and I'm not an expert on that part of the sort of mathematical theory, but the general flavor there is the more flexible you become, the less results you get. I mean, this is a typical thing.
That's typical.
Yeah.
Well, Knuth-Bendix, if you have a set of term rewriting rules, for some sets of term rewriting rules, you can use this Knuth-Bendix completion procedure that will give you another set of term rewriting rules that are, in some sense, are optimal. But you can't do it for every set of term rewriting rules. And I don't know how that, I mean, there's a whole body of theory that I don't know how it extends to graphs and hypergraphs and all that, but that is one. In fact, recently we've been playing around with trying to synthesize rules, based on examples, like rewrite rules. Like, okay, we know that this rewrites to this, or here's a bunch of examples. Okay, well, what are the rules? Synthesis of the rules themselves, and been doing like relational synthesis of rules for trying to do Knuth-Bendix type things. So Arunava is a student I've worked with who's done a project on that. So all these things are deeply connected. Okay, so it's, in fact, now with the nominal stuff, it turns out the nominal logic, the full nominal logic in some senses seems related to set constraints. We've been implementing set constraints, so Nada and Nen and Rafi Sana and I have been working on the set constraints. So turns out set constraints are isomorphic to nominal logic, which is the foundation of alpha rewriting for capture avoiding substitution. And like all of these things are connected. Okay. Yeah. It's hard to find two areas of this sort of computation that don't somehow have relationships.
Very cool. Well, thanks so much for that. That was a great exploration. I think coming from a programming side, you just you program stuff and stuff happens, but getting an appreciation for the theory behind things is actually really fascinating. So this was very illuminating in that regard.
If you figure out how to use hypergraphs to avoid problems with conjunction not being commutative, let me know.
Okay.
Yeah.
Definitely, will do. Great.
Okay. Thank you.
Thanks so much. Okay.
William.
Thanks. Bye-bye.